Hi, everybody. Welcome to Under the Integral Sign. This channel is going to be dedicated to proving integral formulas using the Leibniz rule for differentiation under the integral sign. So I thought it appropriate for the first video to show a proof of that rule. Because if we're going to be using it, we better understand why it works. Okay, so the first step is we're just going to define a function of t like this. And this is going to be a function of t because if you integrate a function of x and t with respect to x and then plug in functions of t for all your x values, you'll just get a function of t. All right. So the next step is we're just going to use basically the limit definition of a derivative. And we're going to substitute our f of t into that. So we'll get that f prime of t is equal to the limit. We'll get this. Okay, we're just using the limit definition of a derivative on our f of t, and we get this. All right. So next, what we're going to do is we're just going to add and subtract the exact same thing inside the numerator. And what we're going to be adding and subtracting is this thing. So we're going to add and subtract that exact thing into the numerator, and then we'll regroup and we'll get this. Go ahead and pause the video if you want to follow that more closely, but I just want to move along. And then we're going to use this property of integrals. Basically, the integral from C1 to C4 is equal to the integral from C1 to C2 plus C2 to C3 plus C3 to C4, and that can extend indefinitely. So we can write this integral, which we have as part of our f prime of t right here, as the integral. We can rewrite it like this. Pause the video and verify that if you'd like. But we can rewrite it like that. So that means we can replace this part right here with this. And that's what we're going to do. So where we see this, we will replace it with this. And if we do that, we end up with this after some nice cancellations. So now we've just reduced our f prime of t to this thing right here. So next, we're just going to kind of regroup it. We're going to, we're going to regroup it so that all our bounds that involve a t plus h are over here, and the parts that don't are over here. So we're just rewriting it. That's nothing special there. All right, so now we're going to use this property that the integral from C1 to C2 is equal to negative integral C2 to C1. So we can write this like this, and that's exactly what we'll do. And we will replace it in our definition for f prime of t. So now we have this. All right, so next, we're just going to split this up into two separate limits, and that should be no problem. The limit of this is just equal to the limit of this plus the limit of this. I mean, no big deal there. All right. So for the second term, since a and t and b and t are constants with respect to x, we're just going to bring that limit like right inside the integral sign, because remember what an integral is. It's a sum. And the sum of a limit is equal to the limit of a sum. So we're just going to bring that limit right inside. And then notice that this is exactly the limit definition of a partial with respect to t of a function of x and t. So we can just rewrite it like this. So this part right here just becomes the integral from a of t to b of t of the partial with respect to t of our function of x and t. Okay, so now the next part. All right, we're going to apply the mean value theorem for integrals, which states that if f of x is continuous on a closed interval a to b, then there exists some c on that interval such that the integral from a to b of f of x dx is equal to f of c times b minus a. That just means there's going to be some point where you can create a rectangle underneath that curve. that's going to be equal to the integral that you're after. Okay, so we're going to apply that to our case. So our case is this. This is our integral. And the mean value theorem is going to state that there exists some C1. We're going to call it C1 because we've already used C. Such that this integral is equal to f evaluated at some value C1, comma, t plus h, times b of t plus h minus b of t. We're just using the mean value theorem for integrals on this integral right here. Okay, now let's think about what C1 has got to be based on the fact that it has to exist on this interval. And don't forget, we're letting h approach 0. So what is our C1 going to approach? If there has to exist a C1 on this interval, b of t, comma, b of t plus h, a C1 has got to equal b of t. It has to. If it's squeezed in between these two things, when h is going to 0, our C1 is going to be b of t. So, we can just say that the integral from b of t to b of t plus h of f of x and t plus h is more or less equal to f of b of t comma t times b of t plus h minus b of t. Because don't forget, this C1, since it's crammed in between, it's crammed on this interval that is infinitesimally small, since h is going to 0. C1 is going to approach b of t, so we're going to say that this integral right here approaches this value. So we can replace our C1 with a b of t, and therefore we can replace this integral with this value right here. I hope that makes sense. Okay, and then we're going to do the exact same thing for this part right here. All right, so exactly the same concept, no change. We're just using C2, you know. All right, so we substitute that back in and we get this. All right, so what does that mean? So if we take the limit as h goes to 0, all we end up with is this. The limit as h goes to 0 of this term right here, which you'll see is right here, is equal to b prime of t. That's the limit definition of b prime of t. And you will get that. You will get that out of it. If you split this up, you'll get f of b of t comma t times the limit as h goes to 0 of this over this, and that's b prime of t. Similarly, this is a prime of t, which is right here and here. All right, so we're going to use that. So therefore, f prime of t is just equal to this right here. That's it. And we're done. I mean, that's it. That is the Leibniz rule for differentiation under the integral sign. And that is the rule that we are going to be using to derive a bunch of really cool integral formulas on this channel. And these are formulas that typically you would not be able to derive without techniques like contour integration, Fourier series, things like that. But we're going to derive them using nothing but this rule. And really quickly, I want to note that we will not be using this full Leibniz rule for differentiation under the integral sign, we're going to be using a version of it where the bounds of integration are constant. Now think about what that means. If the bounds of integration are constant, what is b prime of t going to be equal to? It's going to be equal to 0. Similarly, what is a prime of t going to be equal to? It's going to be equal to 0. So we can say that the derivative with respect to t of the integral from any constant to any other constant of f of x and t dx is just going to be equal to this part right here. And that's the part we're actually going to be using for the majority of these of the videos coming up. Well, anyway, guys, I hope you enjoyed that, and I hope you stay tuned because we're going to develop some really neat formulas. Like I said, formulas that cannot be derived using any other technique. Basically, they can't be derived unless you know some really advanced mathematics. And I know this was kind of advanced, but I'm pretty sure that anybody with a background up to Calculus 2 could probably follow this. So we're just going to use this rule, the Leibniz rule for differentiation, under the integral sign to prove a bunch of really cool integral formulas coming up. So stay tuned. Hope you enjoyed that, and we will see you next time.